Okay, let's start. Okay, I'm sure you have learned differentiation before. It's not new, but we do want to learn a little bit more after all A-levels, right? I must learn a bit more. Okay, before I start, I will introduce this idea of limits. Okay, limits. Okay, my notes work like this. I don't know whether it's the same for previous lecturers, but my notes work like this. Those in black are those printed for you. Those in blue will be those that you have to copy. Can? Okay? Now, suppose we have this expression called 5x minus x squared. We let x approach 2 from the left. From the left means what? Means you have 1.99, 1.999, 1.9999, that kind of thing. Okay? What do we write? We write x approaches 2 from the negative. That means 1.9, 1.99, 1.999. That means we will let x approach from the left. Now you can obviously use your GC to do this. I'm not going to go through the GC strokes, but you can actually construct a table to let the GC do this. You realize that sorry, I forgot to bring my laser pointer today, but you realize that as x approaches 1.99999, approaches 2, you realize that your 5x minus x squared approaches obviously 6. You think so obvious, right? Why Mr. Wu spend time doing this? Okay, never mind, we will go through a bit more later. Similarly, if we let x approach 2 from the right, that means from 2.1 closer and closer to 2.00001, you realize that the value approaches 6. It's far too obvious. I don't want to spend too much time. Now, how do we write? We write this, the notation works like this. If you let it approach from the left, limit, okay, this means what? This means what is the limit of this expression called 5x minus x squared. Okay, how I read this, okay? Stupid, I forgot to bring my laser pointer. Never mind. And I'm not tall enough to reach. Okay, never mind. The limit of that expression as x approaches 2 from the left hand side, 2 negative means 1.99999. Follow what I'm saying? Is obviously 6. Okay? Does it make sense? As it goes closer and closer to 2, that value approaches 6. You will think it's far too obvious. Okay, I know. Okay, so stupid. Similarly, with the right limit of this is also 6. Now then you say, Mr. Wu, it's far too obvious. Whether it's a left limit or the right limit, surely it's the same. Okay, then we say, okay, fine. If they are the same, then we write this. Don't need to put plus or minus. We just say limit as x approaches 2 is 5x minus x squared. Okay, a bit of definition now. So the right limit is this when it's a plus. The left limit is a minus. Just how we say 2 minus 2 plus, right? Left limit and right limit. Now, if the left limit and the right limit are the same, then we don't need to, we will omit the left and the right. We will just immediately say this. The limit exists and the limit is k. Okay, can you ask me? Of course, left and right limit must be the same. How can the left limit and right limit be different? I challenge some of us to think of an example where the left limit and the right limit are different. Actually, they are. They are. You can think of them. The right limit and the left limit are different. Okay? Okay, maybe I give you bonus I give you you think about it. Think about this expression limit of 1 over 1 plus 2 to the power of minus 1 over x as x tend to 0. This limit does not exist. Okay, I shouldn't say does not exist now. You can try. Some of us can key into a calculator. That means your left limit of this and your right limit of this are actually different. You can try. So if they are different, then you cannot say the limit exists. Okay? If they are different, you cannot say that. This is a counter example. Okay? I'm not going to go through in depth, but essentially, I would just say that most of the left limits and the right limits are the same. Let's look at the next page. Obviously, they are the same. For this expression, it's the same because whether you approach from the left or the right, it will tend to the value 6. No problem. Quite easy. I do not intend to go through. But is it always true? See, how do you find the limit for this one? How do you find the value 6? You actually substitute 2, right? You substitute 2, which is 5 times 2, which is 10, minus 4. You get 6. Done. But is it always true that the limit is always just blindly substituting the 2 inside? May not lah. I give you an example. What is the limit of x tend to 0 sine x over x? Now you sub 0 in, your numerator gets 0. Correct? You sub 0 in the denominator, you also get 0. What is 0 divided by 0? It's not 1. You talk about 1. 1 cannot be 1. Something divided by 0 cannot. Okay? It's not 1. But what is it? Okay? So if you blindly substitute 0 into the expression sine over x is undefined, but actually the limit is. I'll let you find out. Okay? Okay, this is the boring bit. Okay, be caution, be careful. It is boring. Okay? But boring doesn't mean that we don't listen. Okay, I want to elaborate a little bit more. You all have learned differentiation. Let me see you. O level. Okay, just test a bit. Differentiate. Do you all know how to differentiate x squared? What is it? 2x. Hey, wait, x over 3. Who's it? Wait, has anyone proven? Thank you. Has anyone proven to you this formula? Very smelly, this thing. Let's change it. Cannot take it. I don't know why other lecturers can take it. Hello? Okay, can. Okay. Anyway, what I'm now about to do is to prove that thing. Okay? Why that thing works. Okay? Differentiation from first principle. Now, okay, let's assume we have one point. Listen up. I think at this point some of you will fall asleep already. I have one point P, x coordinate x, y coordinate is fx because this is the graph of y equals fx. I let another point Q where it's a short distance delta x away. Right? So the x coordinate will just be x plus delta x. The y coordinate will be, of course, f. You all learn functions, right? Tutorial finished already, right? F x plus delta x. Okay, please, all the best. Okay, all the best, okay? Okay. Does it make sense to all of us? Thank you. Does it make sense to all of us that if I join P and Q, the gradient of PQ is actually this distance. Whoa, what just happened? Divide by this distance. Correct? Which is delta y divided by delta x. But delta x, no problem, I can leave it there. This is just the delta x. This delta y is actually the y coordinate of this minus the y coordinate of this, which is this minus this. Make sense? Make sense? Yes? Yes, okay. Now is the important concept. if I move Q closer and closer and closer and closer to P, the gradient of the chord PQ, see, imagine, okay, let me draw this out. Now I have PQ. I have this gradient. If I move Q, here, I have this gradient. The closer Q is to P, the gradient of the chord PQ will actually be the gradient of the tangent at P. One more time. I use a, wait. I like to use this. What do I mean? That means this. Like that. I have P here. Actually, the tangent is this one, correct? This is the gradient of the tangent at P, right? Now, I have a point Q here. And then I try and find the gradient of this one. Now, my Q is quite far away. If suppose my Q is stupid okay, whatever. Okay? Suppose my Q is here. Then the gradient is of this is like, if my Q is closer and closer and closer to P, the gradient of the short chord will be actually the gradient of the tangent at P. Does it make sense? Okay. And it must be super close. So close that delta x tends to 0. Now you know why I talked about limits just now. That means if Q must be super close to P such that your delta x is super small, then it will be the tangent at P. So that's what I was talking about here. As Q tends to P, delta x gets smaller, then this is the most important line. The chord tends to the tangent at P. So does it make sense to all of us that the gradient at P, whoa, cannot show you all this. Okay, I don't know why it's open suddenly. The gradient of the curve at P is actually this idea of the limit of this. The limit of your, this is P, this is Q. As Q gets closer and closer, here, this gradient is actually the gradient of the curve at P. Which is what we are familiar with, which is dy dx. Okay. If you understand this, shall we then attempt to prove from first principle, differentiate x squared, why is it 2x? Why is it 2x? Let's try again. Okay, let's do this. Differentiate from first principles the x squared. Now, first we must understand this. This is from above. That means, stupid, I really forgot to bring my laser pointer. This time I must remember. That means this. You have your delta y divided by delta x. Correct? The idea is this. You have an x squared. Correct? You have a P. You have Q. This is delta y, this is delta x. As Q gets closer and closer to P, your delta x divided by delta y is actually your gradient at P. Okay? Make sense? So, from above is this. Now, but what actually is f? In this case, fx is x squared. So let's rewrite this. It means delta x tend to 0. See, fx is x squared. Fx plus delta x is x plus delta x holding square. minus x squared divided by delta x. Make sense? Make sense? Then we expand it. You get x squared plus 2x delta x plus delta x whole thing square minus x squared. Then you realize that x squared and x squared goes. And then you get this. And then your this one and this one cancels. Then you get this. Now, then you see. Then you see carefully. What happens if your delta x tends to 0? That thing becomes 0. Your answer will then become just a simple 2x. I have just proven that formula that you have accepted as the absolute truth in your O levels. Correct? Differentiate x squared to get 2x. Follow what I'm saying? Okay? The main idea is this. I just want to go back to that diagram again. Have you ever finished copying? Yes? I just want to go back to this idea that as Q tends closer and closer to P, that chord, the gradient of the chord, is actually the gradient at a point of the tangent at point P. So what's it good? Okay, good. Okay, let's do one more. Sine. Okay, let's do one more sine. Then after that we do EX, then we have a short break. Okay? A bit of copying here. If fx is sine x, fx plus delta x is sine x plus delta x minus sine x. Okay? Now at this point then we have to use our, what do we do to simplify? I will have to bring up our MF 26. Where is my MF 26? Look Now, there is this formula here. Let me zoom in a little bit. Sine P minus sine Q is this. Okay? I will, wait I copy this. I paste here. Okay. What hyperlink base? Wow, so advanced. You more advanced than me. Okay. There. Okay, there's this formula for MF15 that says this. Sine P minus sine Q is this. So this is for MF15, MF26, sorry. So this is sine, I let this be P, I let this be Q. Okay, don't care how I get that. This is from MF26. You all should know this. Okay? 2 cosine P plus Q over 2 is X plus delta X plus X over 2. And then you have a sine P minus Q over 2, you get X plus delta X minus Q over 2. You all complain. Very good. Okay? Just blindly using the formula. Don't ask me why I want to use the formula lah. Just copy lah. Okay? Eventually you will realize that I'm just trying to prove why differentiating sine x will get cosine x. Okay? Alright, next line. Now what happens is x plus x divided by 2, you'll get 2 cosine x plus delta x over 2. And if you have a sine, this minus this, you cancel, you get delta x over 2. What I want to do is this. You notice that there's a delta x over 2. I want the delta x over 2 to appear here. So what I will do is I divide numerator and denominator by 2. My next step is this. I divide numerator and denominator by 2. I'll get the 2 goes. I divide numerator and denominator by 2. I shouldn't say this. Anyway, you're right. Divide numerator and denominator by 2. Okay? Okay, the tricky part is this. Now, from this line to the next line is this. I'm splitting up the limit. Actually, you have 2 different functions. You have this function and you have this function. Correct? You have this function and that function. Now, I can simplify or find the limit separately. That means this as x delta x tends to 0, I get cosine. And then I get x delta x tends to 0, I get this. I split them up. Follow? Yes? The idea is this. Okay, I use a different sheet. That means this. Limit x tend to 0 of fx gx is actually limit x tend to 0 fx times limit x tend to 0 gx. So I separate them up. That's the idea. So, now this one is not difficult. Can I have attention, please? Oh, good. Now that's done. This one is not difficult. Can I have attention? Thank you. As delta x tends to 0, you get cosine x. What happens to that? And this is the question I gave you just now, right? What happens when you have sine x over x? You get 0 divided by 0, right? But if you use your GC to calculate this one, this screenshot here tells you this. L1 is your x. L2 is your sine x. If you evaluate the value of sine x as x tends to 1, as x tends to 0, sorry, you realize that limit, must write down, must copy. You realize that as theta tends to 0, sine theta over theta is actually 1. If you use your GC to calculate. I know it's a bit dry. Okay, it's a bit dry, I know. So that's why I drink water. This is not chronograph, really, I don't know. Okay, all right. Let's go through very quickly. Okay, then in the end you get cosine x. The main objective is to tell you that it can be shown, your formula can be shown. Differentiate sine x, you get cosine x can be shown. Okay, I do not then intend to go through this one, you just copy. You're going to read on your own. Okay, I don't intend to copy. Let you all just copy. If you've got time, you just go and read. Okay. Okay, time for a short break. Ayo. So boring. Now all wake up. Best, y'all. Oh, wake up, very good. Hey, wait, you want to... Hey, wait, cannot. Must stop the video lah.